Good morning, everyone, and welcome to Autodesk Virtual Academy. I'm Nigel Lembayek, your host for today and all days. Today, I'm joined by Matt Bussey. How's it going, Matt?
Good.
Usually, Matt's not in the office, so it's really nice to see Matt today for this AVA session. Really important that we could get him here in the office so he could talk to you guys about something we think is really important. And as you can see on the screen here, that is sheet metal unfold rules. Matt is one of our senior solution architects here at KETIV. Matt actually came to us from Autodesk. Matt had worked on the development team there for a number of years.
That's right.
One of the things that he worked on was the current iteration of sheet metal in Inventor. What better person to talk about some of the unfold rules and the theory behind sheet metal than the person who helped put it in the product itself. So thanks, Matt, for being here today and for being part of our team. So Matt is one of our solution architects here on the team. Matt works a lot in regards to helping our customers figure out their automation needs and how to achieve, expediting their processes out the door, whether that's automating things like the modeling process or the dimensioning process, or even other crazier things in Inventor. Matt's the guy to be able to figure that out. So if you have any further questions about even any of that stuff, we'll go ahead and type those into the chat at any time. So before we get started, and Matt shows this awesome presentation, just want to go over a couple of things, set some expectations before the webcast. And Matt, if there's anything you want to add here, definitely go ahead and interject. So today we're going to be going over some sheet metal unfold rules. We're not going to be going over how to actually use sheet metal, right? This is going over, the numbers, the theory behind how all of this is created, right? There's a lot of terminology to be used. There's some math. Matt will show off some awesome math later too. But if you're looking on how to actually use the sheet metal commands in Inventor, this is probably not the AVA that you'll see that in. We've done a couple AVAs in the past showing how to actually, pick and click sheet metal commands, so on and so forth. But this serves a different purpose. We don't want people to go blindly into sheet metal, create like standard for the companies without understanding some of the stuff that Matt's going to be going over today. Things like K-factor, things like bend allowance, bend deduction. All of these are words that get thrown out all the time. And I hear a lot of them on support calls. Go ahead, Matt.
And quite often, a lot of these terms get used interchangeably when they shouldn't. Yes, I've visited a lot of customers over the years, and I'm an old sheet metal guy myself. And, it's quite, it's amazing how many people, especially designers, will come in and they really don't know the background of this is how a flat pattern actually needs to be calculated. So a lot of what we're going to do today is talk about this is the theory behind generating those flat patterns. This is why you use it. This is how you get the values that you use and the reasons you want to plug them in the way that you do.
Awesome. Cool. So with that, I'm going to go ahead and let you get started here, Matt.
Yeah.
And we'll see you on the other side.
Okay. So again, as Nigel said, here's a warning. There's math ahead. There will not be a quiz. You don't have to worry about that. But a lot of what we're going to be talking about is the theory behind how unfold rules work and how Inventor allows you to use that theory. So we want to make sure that we have a foundation of what the theory is, what the math is behind it, because a lot of things that you end up seeing in different shop floors or even in different regions around the world, they all do relate to each other in the background. And so understanding how all those relate and how all those were developed can be very helpful in terms of making sure that you're just using them properly to get the flat pattern out that you need. So let's talk about first of all, just a high level, what are unfold rules? So when you're actually manufacturing a sheet metal part, typically you're starting off with a flat piece, which is the flat pattern or the flat, and you're folding it up, bending it into the shape you want. But in terms of the CAD process, we're going the other way. Typically you're designing the bent or the folded part, and then you need to figure out what the flat pattern is so you can give that to the shop floor, because they've got to cut it out, do the punches, and then do the bending typically, okay? So the way that flat patterns are typically calculated is there's an assumption that for each bend, you can actually unbend it, and you have a what's called a neutral line there. The neutral line is what you see the dotted line here, typically, and this is what your textbook would typically have, is that this neutral line right here, the curve length in the bent or folded should be equal to the length when this is unfolded. And so that assumption is the basis of all unfolding and all flat pattern calculations. And so given that assumption, how do you actually find where that neutral line is? How do you tell Inventor or tell whatever you're using to generate your flat pattern, or even if you're doing it manually, how do you know what that is? Well, this is where the unfold rules are. And for Inventor, basically what we do is we tell it where that neutral line is by giving it a percentage. And the percentage is the percentage of the thickness of the part. And that percentage is known as a K factor. Now, Inventor didn't invent this. This was something that actually got invented by Lockheed Martin back in the 1950s and became a standard practice. And so the K factor is basically a percentage. It goes from 0 to 1. If it's at 0, that means you're on the inside of the bin. And if you're at 1, you're on the outside of the bin. And Inventor has several different ways that you can come in and tell us where that neutral line is. And that's what we're going to be talking about. By the way, just as a note, you can have K factors that are less than 0, and you can have K factors that are greater than 1. Now, in a typical regular bin, you wouldn't need that. But for things like roll-formed shapes, they can be true. And so if you have interest in roll-formed shapes and want to understand how does K factor relate to that, shoot us a message, and we can talk about that as a topic at some other time. So how do we actually get the K factor? Well, let's talk about mathematically first how the K factor relates. And I'm not going to go through all this math, but again, we talked about you have the neutral line, and basically what you want to say is the length of the neutral line when it's curved is equal to the length of the neutral line when it's flat. So L equals L1 plus L2 plus Ln. Okay. Ln, you got all this fancy math that you can do right here to actually calculate what it is, and it's based on your bend angles and your radius at the neutral line, et cetera, et cetera. And basically, you have this little t. This little t is basically a percentage of the thickness. It's the K, in the K factor, all right? And that K factor is typically between 0 and 1. So if you want to find out the length of neutral line, which is really what you're calculating to calculate your flat pattern, this is the formula that you need. So you have all these pieces. You have the bend angle. You have this radius. You have the thickness of your metal. But how do we figure out K? This has always been the mystery. And we used to joke about this internally on the Inventor development team, that K factor is the wonder fudge factor. A lot of us know what fudge factor means. It's some factor that someone has come up with somewhere because there's no way of actually calculating it directly. K factor is determined experimentally. It's like if you go back to your old engineering strength of materials days, it's like Young's modulus. It's like Poisson's ratio. All of those things, we usually have textbooks of saying these are the values, but those values were figured out experimentally. Someone bent a whole bunch of sheet metal parts to come up with a K factor. So it depends. So K factors depend on the material properties. So what's your thickness, what's your strength of materials, what's your hardness, and they can also depend on what your tooling and bend properties are. So how much you're actually bending. What's the radius of the bend? What is the type of bend operation? Is it a brake press? Is it an open air bend? Is it a die? Those can all influence what the actual fudge factor really is. Now, a lot of people are familiar with the default K factor, famous 0.44. That was determined by Lockheed Martin back in the 1950s. They did a whole bunch of experiments, and it was actually, I believe, on cold rolled or spring steel. And they generated, as you can see on the right, these are bitmap images of 3 pages of a several 100-page manual of bend tables.
Yay.
Yes, I actually have the PDF of this somewhere. It's somewhere on a literally a floppy disk somewhere. I'm not even sure I can read it anymore. And so part of what came out of that effort that Lockheed Martin was doing back then to get more accurate sheet metal manufacturing is they came up with an equation, and the results of the equation basically came up with what we know as the default K factor. Most likely, I've done a little bit of research on this. I haven't been able to really find out why, but most likely it was something where they came up with, we don't want to have bazillions of tables to look up. We don't even want to have an equation. What's something that's a rough average that works for us? That's probably how this came up. What's funny is that for a lot of simple manufacturing where tolerances aren't necessarily a big deal, this default K factor tends to work for a lot of people, and that's okay. Nothing wrong with that. But for a lot of people, it doesn't. Especially if you look at like precision sheet metal manufacturing for, say, like the internals of a phone, you need something a lot more accurate than 0.44. And so that means you have to figure out what your K factor needs to be. Now, K factors are determined experimentally, and in the simplest way, the basic way to do that is you take a part that's flat, you measure it, and then you bend it up to a certain angle with a certain radius, and you measure it again. But the math, let's go back to the math here real quick, or let's go back to at least the diagram. You notice that to calculate our general K-factor, what we have to measure is length 1 and length 2 of our two flanges, and we have to measure the overall length, right? The overall length's easy. That's when it's flat. But, you know, putting a ruler up to a bent piece of metal and actually finding where your bend ends and your flange begins is not very practical. So what ends up happening in terms of determining a K-factor is more often is you do something like this. You measure to what's called the virtual sharp, okay? Some of you who made dimension drawings with bends know exactly what I mean. But basically, you've got to measure down to where a ruler can actually hit the table. Again, this is oversimplifying it, but gives you the basic idea, okay? So this is what we're doing is we're measuring what can be called the bend deduction. So bend deduction is basically, look, I can measure from the end here all the way out to this virtual sharp in some way, okay? Or in this particular case, let's see, you're measuring out to right there, okay? So basically what this ends up happening is that your formula changes. It's no longer L1 plus L2 plus the length of the neutral line. Basically what we're doing is saying I can measure LA, I can measure LB in my folded state, and I have to measure, and then basically what I have to figure out is how much do I deduct from that, because the two of those is always going to be longer than your unfolded length. So I have to actually measure what the bend deduction is, okay? So basically that means I have to know what, for LA and LB, they're related to L1 and L2, okay? And they both happen to be that length of that flange plus what we call the setback, okay? And this formula down here is a setback. Now, I don't expect anyone to know this. You don't have to enter this into Inventor. But if you are doing your own measurements to figure out your own K-factors, this is the way you have to do the math, okay? And this is what Inventor expects. And the reasons I'm showing you this, Inventor actually has a lot of this built into the background and the reasons that they do, okay? So from there, there's a whole bunch of other ugly math, but basically once you know that setback, you can figure out a K-factor, okay? So again, experimentally, if you're having to do this yourself because you're finding that, say, something you're getting out of a book doesn't work right, and you have to run your own simple set of experiments, this is the way you go about doing it. I don't expect you to do this, but this is how you can.
Also don't expect them to do thousands of experiments.
No, we don't expect you to do thousands of experiments either. But again, knowing that this is how Inventor sets up its unfold rules is because of this background. This is the way it has practically worked over the years. This is the information that's out there. We have to be able to interpret that information and use it properly, okay? And we want you to understand where the information comes from too, so you can troubleshoot anything that you may be having issues with. So, but seriously, how does this really relate to Inventor? So Inventor Unfold Rules takes this history of how you can actually calculate what ends up becoming the length of the neutral line so that you can actually calculate your unfolded total length to get your flat pattern the right size, okay? So we added capability in Inventor to handle these different types of situations, okay? So for most people, a simple K-factor works. You get something out of a book somewhere, or you just say, hey, 0.44 has always worked for me. Great, that's fantastic. That's all you need to worry about, okay? We do have customers, and I've worked with customers that actually have created their own bend deduction tables, okay? Now, they wouldn't be as extensive as things like Lockheed Martin did, but, you know, they may have like 2 Excel spreadsheet tabs full of information that gives them what they need, okay? But do they want to take all those and do the all the calculations to experimentally figure out, okay, what's a K-factor that reaches these, that is a compromise that averages all these out? Not necessarily. So if they already have the table, we can use that in Inventor. So you can take your bend deduction tables and actually put them into Inventor directly. Now, in between those two, and you see this a lot in Central Europe, there may be something more sophisticated than just a constant and a lot less sophisticated than a bazillion table entries. And that's where we get into equations. So the third way that we handle this is with unfold equations. And these equations are very flexible. They can even be nonlinear, which means if I have an angle between like 0 and 90, use this equation. Between 90 and like 180, use this equation. And anything after that, use something else, okay? And we're gonna go through some real world examples of this that you can see this is why you would use this in Inventor, okay? So let's look at those. So K factors, again, bend allowance. There are a lot that are out there that can be used, and they work for a lot of customers, a lot of people. Generally, what ends up happening is that if you need more than one K factor in the same part, what you do is you create an Inventor unfold rule for each of those K factors and then assign it to each bend that needs it.
Yep.
And so, but for example, like we said, the Lockheed Martin bend allowance, this formula on the right is basically where it came from. I do not remember exactly where all these numbers came from either. I'd have to go back and look at the reference document to remember for sure. And you can see down the bottom, if you screen capture that, that's the original reference that I found it in. Machinery's Handbook also has K factors. Oh, before I forget, Lockheed Martin, I believe that this K factor was meant specifically for either spring steel or cold rolled steel. Again, I'd have to go back and look at the references for sure. So if you're using this for, say, like aluminum or brass, probably not the best K factor because those really do have different physical properties, okay? But like I said, Machinery's Handbook has ones, and again, I've actually used some of these in real life when I was a real engineer back before my Autodesk and KETIV days. And these look pretty well. And again, they tell you where the length of neutral line is, and these K factors, you know, they're pretty reasonable in my opinion. For angles under the 90 degrees, they want you to multiply the bend allowance by the bend angle in degrees. So I don't forget why Machinery's Handbook has this in there. So this gets into, well, hey, how do I handle that? If I say I'm up to 90 degrees, I have one K factor, and after that I've got another. Well, guess what? This is where we get into the equations. But here's an even more sophisticated version of this. DIN 6935. If you've ever had to work with Central Europe, for people who do sheet metal manufacturing, you have to live and breathe by this in many cases. This is a DIN standard that is used for sheet metal parts. I do not remember specifically for what materials it's defined for. I'd have to look that up again, but it's used a lot in Central Europe. And this is something called bend compensation. Bend compensation is actually the negative of bend deduction, just so you know. And so in the way that DIN defines this. But basically DIN defines three different formulas for the bend deduction or the bend compensation. You know, it says, hey, if my angle is from 0 to 90 degrees, use this thing. If it's between 90 and 165, use this thing. And you know what? If I'm barely bending it, it's so close to the original length, don't bother. It's 0. Okay? This K DIN right here, this is not the same K factor as what we've talked about earlier. I have no idea where this flesh factor came from in terms of the DIN standard, but this is what they use. And so one of the things when I was working on the Inventor sheet metal, one of the big items that always came from Central Europe is we've got to be able to handle this because before my tenure on sheet metal, we could only do K factors or bend deduction tables, and neither of those really worked for this formula. So this is why we have formulas in there. This is a really complicated version of it, but you can use these formulas to do things like a just simple K factor. So if I'm between this and this, use one K factor. If I'm between this and this in terms of bend angle, use another. Okay? Bend deduction tables. This is the third way that Inventor can handle unfold rules. Again, this is, look, if you've already gone and done the experiments and you have the tables, you can go in here and just put them into Inventor directly. I have seen some customers that have created their own. I've seen customers that have used ones that they've gotten from other places, again, like Lockheed Martin or someplace else that's already done the work, and they find that those work for each other. The one caveat I will say here is that if you're using bend deduction tables, two things to be aware of. The first is that with older versions of Inventor, and I do not remember when this changed, but bend deduction tables used to always assume that the angle that we're specifying is the opening angle and not the bend angle, while all of your sheet metal features, you specified the bend angle. That has, I know that has changed, like Inventor 2018, Inventor 2019, you can say which set of angles the bend deduction table is actually using. And so I don't, like I said, I don't remember when that change came in, to be honest. And so, but if you happen to be using a really old version of Inventor, definitely something older than like say 2018, 2017, just double check when you create the rule and make sure if the rule gives you an option for bend deduction or opening angle versus bend angle, then you know you're good. But if it doesn't, assume it's always going to interpret the table as being the opening angle. Okay. So a couple last notes on this. Just some of my final thoughts. again, sheet metal terminology tends to be used interchangeably. What we've shown you in this document and what Inventor uses in terms of its actual math under the hood goes by the textbook definition. So what I showed you in this presentation in terms of the equations for bend allowance, that's what Inventor assumes bend allowance means. It's what it assumes bend deduction or bend compensation means.
Yep.
Why I bring this up, especially things like bend allowance and bend deduction on the shop floor, tend to be used interchangeably, meaning the same thing when, you know, from an Inventor point of view, they don't. Now, I've been on numerous shop floors, both, again, when I was doing sheet metal manufacturing and when I was visiting customers, when I was with the Inventor team, where I would look at something on someone's wall and it said bend allowance. And I looked at it and I'm like, those look like bend deductions. And yes, they actually were bend deductions, and vice versa. So, you know, when you're talking through this kind of terminology, say, you know, you're on the shop floor and you're looking at what tables they have, make sure that what you're inputting into Inventor is really what Inventor is expecting. Otherwise, you will get incorrect results, okay? Again, so one of the things to talk about, if you have someone talking about bend compensation, make sure that it really is what Inventor thinks bend compensation is, because Inventor thinks bend compensation is the negative of bend deduction.
Mm-hmm.
So again, bend compensation and bend deduction can be used interchangeably. That's closer, that's usually okay, but the negative tends to throw some funny results out if you're not inputting it into your unfold rules correctly. And again, the one last thing that can come up, doesn't come up as often now, but it used to in older days of Inventor. Make sure that when you're inputting everything, especially when you're using the bend deduction tables, that you are specifying and understand the difference between the bend angle and the opening angle. And this image on the right in the presentation shows you what Inventor assumes those two are. Yep. Okay. So your opening angle really is really measuring the angle on the side where your inside radius is, and your opening angle, or and your that's your opening angle, and your bend angle really is this angle right here. Okay. So this is relatively quick. This is kind of a whirlwind tour of this. There's not a lot to this, but one of the things we want to do next is we want to say, look, you got any questions? And do you have any questions of exactly how does this end up getting applied in Inventor? And we can, I am great at doing on-the-fly demos that don't work.
That's awesome. So one thing that I wanted to bring up too is a question that I got from somebody earlier this week that I told them, hey, like, come watch this. Is what happens when you have one part that's being bent by multiple machines that may have different K factors? What do you do in Inventor?
This is not easy. I will admit that. Really what it comes down to is where do you actually assign the unfold rule to a bend, okay? So let's take a look at this sample part right here. If I come in here and I edit the feature on each one of these individual flanges, you come in here and you have the unfold options, okay? And this is where you can actually specify the unfold rule for the bends in that flange. Notice I said bends with an S. So if you create a single flange that only has a single bend, really what you have to come in is you have to come in and start saying on a feature by feature basis, this is the unfold rule to use. No question that this is tedious. This was one of the things that I personally had on my wish list that I wanted to get fixed in Inventor that we just didn't get to. Okay. And I would love to see this. What's the current wish list mechanism for Autodesk? Right,
the Idea Station?
The Idea Station. Thank you. I couldn't remember the name. I should know it, but I don't remember it.
Inventor Ideas.
Yeah. I would love to see something like this on Idea Station, because what we'd wanted to see at some point is, hey, select the actual bend on the part or in the feature tree, and basically right-click on it and say, set unfold rule. So you can kind of multi-select things. It didn't happen. I would love to see it, but that's basically what you have to do. Where this starts becoming an issue, and what you have to plan ahead on when you're doing your design is, actually, let me sketch this up. Let me create a new sheet metal part, okay? And I'm going to create a very simple contour flange. Okay. Let me put some relatively reasonable dimensions on here. Let me put this like at 6. I'm designing without a mouse. I'm using my touchpad, so this is going to be a little slow, so give me just a moment.
It isn't slow. It's like amazing, because I if you don't give me a mouse, I'm like completely useless.
I've had to actually do a lot of demos without a mouse before, so I've kind of gotten used to it. It's not my preferred way of running Inventor, though. All right, so here's where this becomes something where you have to plan it out. When you're creating something like a contour flange, you notice in here that you get 2 bends. But unfortunately, the unfold rule is by feature.
Mm-hmm.
So if each of these bends ends up having to be its own K factor, what you basically have to do is you have to come in and build this in pieces. I really wish that that there was an easier way to do this, and there isn't. Not that I remember, but you know what? I've met some clever people who have figured out workarounds to this type of thing. But yeah, basically you have to build it in pieces. So you basically have to build out this part of the contour flange first and give it one unfold rule. Okay. Let me actually create a second K factor in here for a moment, just so we have a second rule to apply. Okay. Let me call this rule 2. And let's say that I'm going to give it a K factor value, say something like 0.7, just something this, you know.
Not 0.44.
That's not 0.44. Okay. And so if I come in here and create the second flange on that one, as I'm creating it, again, I'll have to just give it the second rule. Okay. Right now, that is the only way to really deal with it. So what you need to do is you need to make sure that you, for your designers, define when they need to understand that rule. And sometimes it's not easy up front. It really isn't. What I have seen customers do is say, look, the best way to understand this is know which is going to be an inside fold versus an outside fold, because that tends to be a lot of the typical when I'm on one machine versus another.
Yep.
But other than that, it's really hard to say, you know, what are generic rules to help you with your kind of design methodology. That's the basics of it. You know, one of the things we can help you do is if you have more detailed examples that you need help with us, give us contact us. We can help you work through, kind of figure out a general process of this is how you plan out your sheet metal design to account for that.
Yep.
And I have done that with customers in the past. So.
And you can call Eric Paul. Shout out to Eric, who I know has worked with a couple of our customers who have this exact problem. So.
Yeah, Eric and I have actually worked on this problem together. So. Yep.
All right, let's see what else.
Any other questions?
Have. Yeah, Eric, do you have anything from Eric's actually helping us on the back end today on the stream? So shout out to Eric. Let's take a look. Sorry for the silence, reading through questions. So, long story short, is there a way to use a contour flange and have dynamic bend radii?
Dynamic bend radii. Oh, okay. So this probably comes back to, let me make sure I'm understanding the question correctly. Let me back up on this for a moment. All right, so let's start with this. I think I know what they're saying. This comes in. This is a similar problem to having a different. If I'm interpreting this way, it's a similar issue for, you know, if I create a contour flange like this, and I created it by not putting the bends in or putting the radiuses in the sketch. By default, what it does is that when I give it a bend value. Let's see. Yeah, right here, bend radius. When I give it a bend value, it gives the same bend radius value to each of the bends that it auto-magically adds. The only way to really work around this that I can think of off the top of my head, and I'd have to think about this more, is basically you have to, in your sketch, basically put a fillet in for everything that's going to be variable within the contour. And I know that's not a great answer, but I think, again, that's the reality of it. So if my top radius here should be my default bend radius, and my bottom right here needs to be something that is variable or dynamic, The only way I can think of off the top of my head is I would have to come in and I have to basically put a sketch fillet in here. Okay. And then I would probably give it, and then what I would do is, let me get out of this for a second. I did it a little wrong. I have to do it this way. I would come in here and just say bin rad 1 equals, say, 0.5. You put it in basically as a sketched fillet or sketched arc. You give it, let me change my display dimensions to expression so we can see that. You basically give it a dimension that has a parameter name, and then what you do is you have to basically update that parameter as you would in normal Inventor. When you do that, when you use the contour flange command, contour flange only adds bends when it sees a sharp corner in the sketch. If it sees anything else, it just basically, like in this case, it took the actual arc and it just said, I'm just going to put a thickness on that and extrude the arc. Okay. And Inventor, one of the little inside things about Inventor, when Inventor creates a flat pattern, it's actually using a feature recognition engine under the hood. Now, when we create, like, say, our own bins with Inventor, we put a little something that you don't see. We have a hidden annotation on there, or attribute, if you know the Inventor API, that says this is a bend, treat it like a bend. But other than that, what Inventor does is it says, look, everything that's basically a flat plate is not a bend. Anything that's not, I'm going to assume it's a bend, and I'm going to see if I can unfold it. So even though this is not designated as a bend, when you come in here and you actually create the flat pattern, it's still going to unfold it because it says, hey, it wasn't a flat piece. It wasn't a flat plate. And if it happens to be a geometry that is what we would call analytic, which means, is it a cylinder or is it a cone primarily? And if the answer to those is yes, then it's going to treat it as a bend and it's going to apply a K factor to it. Now, in this particular case, it's applying the default unfold rule. If you have to get more sophisticated where this particular bend needs a specific K factor, that's something that I'd have to do a little bit of research on the right way to do that.
Exactly. Okay? And so if I know that you had mentioned that you already were using something similar to what Matt had showed. If you want to, chat about it further, kind of pick Matt's brain. I know a lot of our customers have been doing that since Matt has joined the team. Please reach out to us. More than happy to set up some time. Matt's, one of the more available people to be able to get into contact with. So yeah, just reach out and we'll make sure to get you all connected. All right. This question got cut off. Let me expand my questions box so I can read the whole message. Expanding on the dynamic radius idea. So this started a conversation. Good. We're experiencing different bend radii based on the angle that the parts are being bent. Is there a way for Inventor to handle this?
Directly, no. This gets back into, let's talk about why you would have a different K factor per bend. Well, it depends a little bit. So let me back up a little bit. The unfold length that gets calculated and the K factor that you need to do that, it depends on several factors, but the most common factors are obviously what material you're bending, like aluminum versus steel. Yep. The second thing it tends to be influenced by is how far you're bending it, so how much of an angle you're bending. The third thing it gets influenced by is what the actual radius of the bend is, which is typically determined by your tooling. Now, if you're actually experiencing a different radius with the same tool, that's something where you're going to have to run most likely some experiments on your tooling and your manufacturing process. And the way to handle it in Inventor is that for each of those types of bends, you have to assign that particular bend a different unfold rule. Okay. But unfortunately, there isn't a way. Inventor can't magically determine what a K factor is. I would love it if it could, but it can't. So if you're seeing that kind of variability in your manufacturing process, and you need to make sure that you are calculating a flat pattern that accounts for that variability, you basically have to go back to basics, just like the guys at Lockheed did many, many moons ago. You got to run some experiments, take some measurements. Once you have those measurements, then plug them into Inventor as unfold rules, and have basically engineering design methodologies. We're saying, if you're creating this type of feature, and we know this is the unfold rule you have to use in this particular case.
Yep.
I wish it was easier and simpler than that. I really do, but that really is the reality of how it has to work.
And then just to follow up to that, can Inventor assign a radius based on, or bend radius based on the angle of the bend? Set up as parameters. You
set up as parameters is the only way I can think of to do it off the top of my head. That's the first thing I would try. The other if it gets more sophisticated, like if you have a problem where the bend radius for some strange reason is not a linear relationship to your bend angle, then you may have to look at something a little more sophisticated, like actually putting in like an Inventor macro using VBA or something like that, or iLogic. Actually, iLogic is probably the way I would do it.
Yeah,
I would go in and I would put some iLogic into my sheet metal template that said, given these rules, if I'm between an angle of 0 and 25, this is the radius I should use. If I'm in the second range, then this radius. I mean, I'm thinking off the top of my head. But if you want to contact us and you have some examples you can send us, we can take a look at it, and we can probably give you a little bit better idea of, hey, here's an approach to try. But off the top of my head, I think that's the way I would start to tackle it.
I think that makes sense based on just thinking as you were, going through that process. It was like, in theory, that should work.
Yeah, in theory, it should work. But yeah, I honestly, I would have to sit down with an example of saying, okay, this is what we're seeing, and then probably play with it a little bit, Inventor to find the most efficient way to do it. Because there are 3 or 4 different ways I could think of how to tackle the problem, but they all have varying levels of difficulty in terms of maintaining them and implementing them. Like if you have to worry about this across like 100 different users, I may do it one way. If you had to do it with like only with 5 different users, I might do it a different way. So
exactly. And then for those people who are asking like what email to send this back to, if you just respond to any of the AVA emails that you've been getting, sometimes they're from me, sometimes they're from Jessica, sometimes they're from like a marketing alias. Just go ahead and reply to that email and say you need some assistance with something, and we'll make sure you get to the right person. Whether that's myself, Eric, Matt, our Lifeline team, whoever, sales representatives, regardless, we can get you to the right person on the team that you need to contact with.
Brian Kelly. Hi, Brian. Brian Kelly and I are old friends. We both worked at Autodesk together. He was my KETIV reseller before, when I was back as a KETIV customer back many moons ago.
Wow, that's awesome. Brian Kelly's here every week, so shout out to Brian.
Yeah.
All right. Will this theory work with wood and what I'm trying to make more conical shapes? I think we need to see it.
Well, let me ask this, because I want to make sure I'm understanding. Because my dad's an old woodworker, and you can bend wood, believe it or not. A lot of that has to do with, if I remember right, soaking wood in water, and it's a slow process, but it can. Theoretically, yes, but how accurate it is, let me go back to a picture here in the presentation. Let's go back to kind of like the original. How does this all come about? This assumption that this neutral line always stays the same, it is an assumption. If you've done any kind of engineering into strengths of materials and how material properties really work, you would know that this assumption technically isn't correct. When you bend metal or bend anything, it is not a linear deformation. So one of the assumptions that gets made in this that I glossed over, but let's talk about it. The thickness in this bent state is exactly the same as the thickness in the flat state. That is not true. When you bend metal, this thickness, let me
I'm hearing this in my professor's voice, man.
Yeah. This thickness right here, the metal thins there, okay? So part of the reason this works really well for metal is that the amount of thinning that happens is so small that the error in making this assumption, it's just, in most cases, it's just negligible. Yeah. It's like tens of thousandths of an inch or less. Okay, when you bend wood, sure, you could use this theory in terms of using K factors, but you have to question whether the assumption holds, is really what it comes down to. And again, it depends on what you're doing with woodworking. I always joke, because I come from a manufacturing background, but I also, one of the things I used to do is I used to work for manufacturing for construction, manufacturing for as built. And one of the great disconnects there is manufacturing wants to be accurate to 10,000ths of an inch. Construction wants to be accurate to plus or minus about a foot.
Depending on how big the structure is.
Depending on how big the structure is, And so, if you look at some gigantic skyscraper, plus or minus 6 inches across the whole thing is probably pretty accurate. So what it comes down to is, sure, you can apply it, but how accurate is it going to be? That I really couldn't tell you. Okay. Again, you basically have to experiment with it.
Yeah, you could try. I think ultimately it comes up to
it comes up to trial and error. So hopefully that answered the question. A little bit roundabout, but
yeah. Let's see what else Eric has. So Eric sent us some questions. We got some viewers from Poland, so I guess it was good to go over some of that European stuff.
By the way, DIN 3, I always get the number confused. That DIN standard is in Inventor by default. Yep. And so, if you look at the default, let me skip out of this. If you go in and you look at the bend compensation, this is the DIN equation from that standard. Almost, purists will look at it and go, there's a couple situations that actually technically doesn't handle, but it handles almost all of them. And so.
Nice. So yeah, if you are working with someone in Central Europe, or you are in Central Europe, because we do have viewers all over the world, like Eric mentioned in the background there, there's a couple people from Central Europe on the webcast right now. It's already in there.
Yep.
So you don't need to input the equations yourself, because that would not be fun.
No, never is.
Cool. I think that's just about it for questions. I'll give everyone another 30 seconds or so to ask any more while I make a couple of announcements over the next couple of weeks. So next week, Alex Alvarez is going to be on with us for AVA to talk about some of the updates in Inventor HSM that have happened over the last couple of months. As Inventor HSM evolves, it's able to do new things. It changes the way it does a couple of things. It makes everything a little bit better. And, saving a couple clicks here and there is always worth it. So he'll go over what's new in Inventor HSM. I believe it's 2019.2. or 1.1, one of the two. It's the newest update for Inventor HSM. They change the numbers on us all the time.
I can't keep track of those either anymore.
Me neither, which is good. It's constant improvement.
Yes.
I'll take it. So shout out to the Inventor HSM team over there for giving us this update. Alex is going to go over what's included in that, and how to use a couple of the new features that are in there. So that's Inventor HSM. If you have any questions, like I said, go ahead and just respond to any emails that come to you from some of these AVA announcements, and we'll make sure to get that information back to myself or back to Matt or whoever on the team is the best person to answer your question. It looks like we didn't get anything else, but again, I'd like to thank Matt for flying a couple 100 miles to come hang out with us in the office this week, be part of this AVA. I'm sure. Super useful. There's a ton of people on here still, so hopefully you all found this really, really useful, especially if you're building some of your sheet metal standards from scratch. I know that's always the most fun.
Yeah, it definitely is. And like I said, I was on the Inventor development team for quite a while, and so there are a few kind of insider AVAs that I've been talking about with folks here at KETIV that we can do. So if you like this, if you like this more insider information, definitely let us know, and let us know if there's some insider type of topics like, hey, I'd like to go more in depth of why does Inventor work this way? That type of stuff.
Yeah.
And if I can give you the inside scoop, I will.
Cool. Yeah, and I think Brian Kelly says it best. Like, this is super nerderific, and I think
Absolutely.
a lot of the people who are on webcasts like this, don't mind seeing a lot of this stuff. So, expect to see more of this kind of stuff with Matt in the future. And then the last question here, you mentioned aluminum. What about copper K factors? So just grab that.
Off the top of my head, I do know that like Machinery's Handbook has a K factor for soft copper. And for hard copper and half hard copper. Exactly how well those in particular work in terms of manufacturing, I have not done a lot with copper myself personally, so I don't know. But
yeah, generally looking these things
yeah.
up in the engineering handbook or the materials handbooks too are going to be able to give you some information. There's literal for aluminum. There's however many different kinds of aluminum there are that many different K factors in some of those books.
Yeah, I believe so. Yeah, but yeah, I tend to go to things like machinery handbook first.
Yep.
Start there and then work my way out.
Exactly.
So.
And then if you're not getting what's expected on your machinery, then maybe do some tests, because I know that all machinery is a little bit different. You might have some stuff. So again, Matt, thanks for being here today. Everyone, expect to see more of Matt in the future. I'm really excited. And enjoy the rest of your week. We'll see you all next Thursday. Bye-bye.
All right. Thank y'all.